Hello, physics students. This is Mrs. Krumschreider, and we're going to do the concept development practice page. You're welcome to do it together with me as we go through this. Number 1. A crate filled with delicious junk food rests on a horizontal floor. Only gravity and the support force of the floor act on it, as shown by the vectors for weight, W, and normal force, N. So N is the floor supporting it, and this is the pull of gravity acting down. The net force on the crate is blank. Alright, so we know that because the object, the crate, is not moving, that means that the net force has to be 0. So evidence for this is that the crate is not moving. So there's no acceleration. Number 2. A slight pull P is exerted on the crate, not enough to move it. The force of friction F acting on the crate is, so here's our force of friction acting to try to restrict the movement of the crate, and here's our pull. So the force of friction acting on the crate is blank P. Okay, well, it has to be equal to P, because again, this crate is not moving, so the sum of the forces has to be equal to 0. The net force on the crate is 0 because it's not moving. Number 3, pull P is increased until the crate begins to move. It is pulled so that it moves with constant velocity across the floor. Friction F is blank P. So if the object is moving this way, then again that means that the sum of the forces is no longer 0. And if it's moving this way, that means that I have to have a net force acting this way. So that means, right, because these are already balanced and it's not moving up and down. So that means this has to be greater than the friction. So friction is less than P. Oh, that would be true, sorry. But it actually is equal to, and the reason it's equal to is because it's moving at a constant velocity. And so that's important because that means, again, that there is no acceleration. So constant velocity means acceleration is 0. The net force on the crate is equal to 0 because the sum of the forces is 0. There's no acceleration. Pull P is further increased and is now greater than friction. Okay. So they've just told us this pull is greater than the friction. The net force on the crate is blank 0. So now it's going to be greater than 0. Okay, because this pull is greater than the force of friction. The net force acts toward the right, so acceleration acts toward the right as well because our net force is to the right, and our equation for acceleration is that acceleration equals our net force divided by our mass. Okay. So, if the pulling force P is 150 newtons and the crate doesn't move, what is the magnitude of the friction? Well, if it doesn't move, we have to have our sum of our forces to be 0, so it has to be 150 newtons. If the pulling force P is 200 newtons and the crate doesn't move, what is the magnitude of the friction? Again, it's not moving, which means the sum of the forces has to be 0, so it has to be 200 newtons. If the force of sliding friction is 250 newtons, What force is necessary to keep the crate sliding at constant velocity? So that's like this situation here, okay? That's what it's talking about. So now we are moving, but the crate is sliding at a constant velocity. Remember, that means that still the sum of the forces is 0. So if friction is acting with 250 newtons, then my force must also be 250 newtons. If the mass of the crate is 50 kilograms and sliding friction is 250 newtons, what is the acceleration of the crate when the pulling force is 250 newtons? So acceleration is our net force divided by our mass. So in this first one, okay, to figure out our net force, we're pulling with 250 newtons this way, based on these illustrations, and sliding friction is 250 newtons the other way. So what's my net force going to be? 0, divided by my mass, which is 50 kilograms, right? And 0 divided by 50 is 0. So my acceleration is going to be 0 meters per second squared. So now our next situation is 300 newtons. So in this case, I have 300 newtons acting to the right. My friction is still 250 newtons to the left. So my net force is 50 newtons divided by 50 kilograms. 50 divided by 50 is 1. So my acceleration is 1 meter per second squared. Lastly, I'm pulling with 500 newtons. My force of friction is still 250 newtons in the opposite direction. So it's going to be 500 newtons minus 250 newtons to find my net force, which is 250 newtons. And then I'm going to divide that by my 50 kilograms. And 250 divided by 50, okay, is 5. So my acceleration is 5 meters per second squared. Falling and air resistance. Bronco skydives and parachutes from a stationary helicopter. Various stages of fall are shown in positions A through F. Using Newton's second law, that the acceleration is the net force divided by the mass. And the net force is going to be W minus R here divided by M. Find Bronco's acceleration at each position. Answering the blanks to the right, you need to know that Bronco's mass is 100 kilograms. So for this, we're always going to plug in 100 kilograms. So his weight is a constant 1,000 newtons. So notice the weight here in every picture is 1,000 newtons. Okay? And air resistance R varies with the speed and cross-sectional area as shown. So again, the only thing here that's changing is the wind resistance, the air resistance. So W, 1,000, minus 0, the R, divided by 100 is 10 meters per second squared. So our next one, 1,000 minus 400 divided by 100 is 6 meters per second squared. Our next one, 1,000 minus 1,000 divided by 100 is 0 meters per second squared. Okay, so again, what this is saying is he's accelerating downward here at 10 meters per second squared. Here, it's slowed down a bit, right? He's not accelerating downward as much, to 6 meters per second squared. And here, he's not accelerating downward anymore at all. His acceleration is 0 meters per second squared. So now we come to our next spot. and our wind resistance, or his weight, is 1,000 still. Subtracting the 1,200 of air resistance divided by 100 gives me -2 meters per second squared. Now, what does the positive in front of these mean? Okay, right? The positive is just the direction, so this means it's downward. Downward. So if positive is downward, what does this negative mean? Upward. Okay, he's actually soaring a little bit here. Okay, we come to our next one. Again, we have 1,000 for his weight minus the 2,000 of air resistance divided by 100 his mass, and I get -10 meters per second squared. So again, his acceleration, he's slowing down, right? He's losing speed. Right, so another way to think about this is up here, he's gaining speed. He's gaining speed. Now he's losing speed. And here he's even losing more speed. Now, that's a good thing, right? Because that's what the parachute is supposed to do. So, here we have him at the bottom. And again, his weight is 1,000. The wind resistance is 1,000. Divided by his mass of 100 gives me 0 meters per second squared. So now, right, notice what's happening here. He's accelerating, okay, and picking up speed as he falls. He eventually reaches a speed where he stops picking up speed, okay? So he's picking up speed here as he falls. He's accelerating, he's gaining speed. Temporarily, he's not gaining any more speed. He's reached his terminal velocity. He puts out his parachute. Now, his parachute does what it's supposed to, right? It slows down his acceleration. So it means here he's actually temporarily losing speed because the parachute is being deployed. And he's losing a lot more speed here because his parachute is out. Eventually, he comes to a new speed, constant speed that he falls with his parachute deployed. Okay? So that's what we see happening here. So now if we look at this other part of this, circle the correct answers. When Bronco's speed is least, his acceleration is. Okay? So his speed is the least, right? Right after he jumps out here, right after he deploys his parachute, and notice his acceleration is the most. In which positions does Bronco experience a downward acceleration? So where is acceleration acting downward? A and B, because those are positive. Number 3. In which position does Bronco experience an upward acceleration? Those are those negative accelerations, so that's in position D and E. When Bronco experiences an upward acceleration, his velocity is, so what they're saying here is here, his velocity, his speed, is it downward or is it upward as well? So is he moving upward or downward? He's still falling, right? So his velocity is still downward. In which position is Bronco's velocity constant? So remember, another way to define acceleration is that acceleration is the change in velocity over our time interval. So at which positions is Bronco's velocity constant? So when does he have no acceleration because there's no change in velocity? Well, that would be position C and position F. In which positions does Bronco experience terminal velocity? Again, that's that maximum speed you can reach, at which point you no longer gain any more speed. And again, that would be at position C and position F. In which positions is terminal velocity the greatest? So their question here is he moving faster here, or is he moving faster here downward? Right, and he's going to be moving or falling faster in position C. So his terminal velocity is greater in position C. If Bronco were heavier, his terminal velocity would be greater. Okay, because his mass would be larger. So that is that concept development practice page. Have a great day. I'll talk to you tomorrow.